Today we're going to continue our discussion of classification, concentrating on decision trees and support vector machines. So recall that the goal of classification is to have machines label data for us. And last time we talked about two techniques that did that, naive Bayes and logistic regressions. This time we're talking about decision trees and support vector machines, which are also examples of classification. Decision trees are fairly intuitive. They're simple techniques that give you classifiers that are actually fairly easy to understand what's going on with them. Support vector machines are another example of linear classifier. I'll talk about what a linear classifier is because it's very important for understanding support vector machines. And we'll see how support vector machines, which are defined using geometric interpretations, can give you state-of-the-art classification. And in class, we'll go through examples in Rattle using all three of these techniques. And at the very end of this lecture and during class, we'll talk about what classifier should you use for any particular problem. So first, let's talk about decision trees. Suppose that you want to construct a set of rules to represent the data, and you can represent these rules as a series of if-then statements, which should be familiar to anyone who's done programming. So here, if splits your data into two sets, one where it's true and one where it's false. And you can represent this series of decisions as a tree. So let's say that you have three features, x1, x2, x3. You can ask a bunch of questions about these features. So if x1 is greater than 5, then you follow the true arrow. Then you ask, is x1 greater than 8? If it is, then you follow the true arrow, and then you apply the label false. And it should be fairly clear how you can see this as sort of pseudocode that you would write in a programming language. So given this tree, let's run some examples. So let's say you have an example where x1 is 1, x2 is 1, and x3 is 1. First you ask, is x1 greater than 5? No, it isn't. So then you ask, is x2 less than -2? No, it isn't. So you apply the label true. Now let's take a look at the second example, where x1 is 10, x2 is -3, and x3 is 0. So first you ask, is x1 greater than 5? Yes, it is. So you follow the true arrow. Then you ask, is x1 greater than 8? Yes, it is. So you follow the true arrow. And then you apply the label false. The interesting thing to note about this is that you didn't look at x2 or x3. You made your decision entirely based on x1. Some of the terminology that we'll use in discussing decision trees are branches and leaves. Branches are one side of a split. So when you ask, is x1 greater than 5, that induces a split. You have a branch where x1 is greater than 5 and a branch where x1 isn't. The leaves are the terminal nodes that return values, so all the places where you get a final answer for your classification. And trees can be used for regression as well. It just depends on what your leaves are. So if your leaves are a continuous real number, then it's regression. If your leaves are discrete labels, then it's a classification. And unlike linear regression, support vector machines, naive Bayes, etc., trees can fit local models. So this means that a tree can break up your feature space in any way that it sees fit. And this results in fast, interpretable predictions. To see that, let's look at an example of the 2008 Democratic primary, where Hillary Clinton was running against Barack Obama. Barack Obama eventually won, obviously. But the task at the time was to ask, given information about a particular county, how will that county vote for either Clinton or Obama? There are a number of reasons you might want to do this. If you're a campaign, you might want to focus your limited resources on getting out the vote in particular areas where you might have the greatest advantage. And it's also interesting from a post hoc explanatory perspective of seeing how different variables interacted in predicting voter turnout. Here's the whole tree. You can look at the PDF online to see this in more detail, but we'll also zoom in and discuss some of these splits. First question that gets asked is the county more than 20% black? If yes, then Obama wins most of those counties. Is the high school graduation rate higher than 78%? If not, then Clinton wins most of those counties. If the county is in the Northeast or South, then Clinton is more likely to win the counties. If the population is more urban, then Obama is more likely to win the county. And if Bush beat Kerry in the county, then Clinton is more likely to win. From this, you can see how we represent decision trees. Each internal node tests an attribute. Each branch corresponds to an attribute value, i.e., the population density being greater than or less than some particular threshold. And each leaf assigns a classification result, Obama or Clinton winning. In class, we'll go through how you would represent simple functions using decision trees. Decision trees are a good choice when you have a very large number of features and where your training data are likely to be fairly noisy, or in cases where you need to represent your final classifier in a way that humans can understand. For example, if you're trying to predict whether someone has a disease or not, and you want your final classifier to be vetted by an expert like a doctor, then a decision tree is a good choice because you can show the decision tree to an expert and ask them to say what they think of the classifier that you learned. Similarly, if you're trying to predict whether someone is a poor credit risk or not, you need to be able to explain the decision to, say, the person applying for a loan. Or if you need to build classifiers from preferences that people need to input themselves, it's easier to represent this as a decision tree. Now that we've talked about how you represent a decision tree, let's talk about how you learn decision trees from data. The way that we learn decision trees is in a top-down fashion. So at each point, we need to figure out what is the split that separates our data into two halves that look less chaotic. And we keep doing that until we reach some threshold of either too few nodes in our split data set or that we've done everything perfectly classified. So given this blueprint, what we need to figure out is what makes a good split of the data. So remember, a split of the data is to split your data set based on some attribute. Here we'll assume that all our attributes are binary for the sake of convenience. So let's say that we have attribute 1 and attribute 2. And we'll annotate each of the nodes with the number of positive and negative labels at the nodes. So attribute 1 can either be true or false. If it's true, you have 21 positive labels and 5 negative labels. If it's false, you have 8 positive labels and 30 negative labels. Is this a better split than splitting on attribute 2? In attribute 2, when it's true, you have 18 positive examples and 33 negative examples. When it's false, you have 11 positive examples and 2 negative examples. What we want is a split that gives us a more coherent view of the data. In a perfect world, we would have a split where if an attribute is true, we only have one kind of label, and if it's false, we also only have one kind of label. So how can we measure this quantitatively? This is where the concept of entropy that we talked about comes in. If you have a binary label, then the entropy over the distribution of that label shows how chaotic this split of the dataset is. If you have a 50-50 balance, it has maximum entropy. If you have all of one label, then you have zero entropy. This is what it looks like graphically, and remember, this is what the equation looks like. We use the definition of entropy to define how much we gain by using a particular attribute. This is called the information gain. How much does the entropy reduce based on sorting or splitting on A? So what we need to do is we need to take the original entropy and then take the expected entropy for each of the splits. We'll work through some examples in class, but here's the general blueprint. First, you take the entropy of the dataset before you split. This gives you the baseline. How much entropy do you originally have in your system? In this case, there are 29 positive examples and 35 negative examples, so this gives us an entropy of 0.96. It's fairly evenly split. So how much gain do we get if we split on the first attribute? For the first attribute, we have original entropy of 0.96. Then we split into two branches. One has 26 examples, the other one has 38 examples. We then compute the entropy in each of those sections, and that gives us 0.96 minus 28 minus 0.44 for an overall gain of 0.24. Now let's look at attribute 2. We have the same original entropy, but it then splits into two branches, one of which has 51 examples and the other has 13. We then compute the entropy in each of those branches, and then we get 0.96 minus 0.75 minus 0.13. So that gives us 0.08. So a much lower information gain. Why did this happen? This is because even though you have one very low entropy branch in attribute 2, the one with 13 examples, that was overpowered by the much more common case of 51 examples going to a relatively high entropy split. When you use Rattle to find a decision tree, it will use something called the ID3 algorithm. The ID3 algorithm starts at the root and looks for the best attribute. It repeats for subtrees at each attribute outcome, and it stops when the information gain is below some threshold. This means that it will prefer shorter trees. This prevents overfitting, something that we'll talk more about later in future lectures. Now that we've introduced decision trees, let's talk about vector space classification.